Once we know how to use implicit differentiation, we then can apply it to other problems. So at the end of this lesson, you'll be able to apply implicit differentiation to other derivative problems. Right, and we're just going to jump right into the examples. You'll notice that this says to find the slope of the tangent line to 4 minus x times y squared equals x cubed at the point 2, 2. Well, we've already learned that to get the slope of the tangent line, that is just actually the derivative. So this problem is just asking us find the derivative at the point 2, 2. So we're going to find the derivative of this function. It's an implicit problem because we've got x's and y's happening both at the same time. So I notice on the left side that we actually have a product going on because I have 4 minus x times y squared. So we'll let 4 minus x be our f and y squared be our g. My f prime, the derivative of 4 minus x, will be negative 1. The derivative of g will be 2y. And then we also have to say that we're taking the derivative of y with respect to x. So if I write that product rule out, it's going to be f prime times g plus f times g prime, and then equals the derivative of the right side, the derivative of x cubed will be 3x squared. Right, I'm going to clean this up just a little bit. Negative 1 times y squared will just be negative y squared. And then this one, we usually like to write the 2y in front of the parentheses, so this will really be 2y, 4 minus x, dy dx equals 3x squared. Okay, and then from here, whoops, there was supposed to be a plus there, sorry about that. All right, and then from here, if I want to solve for dy dx, I will add y squared to both sides. So I will now have 2y, 4 minus x, dy dx is equal to 3x squared plus y squared. And now if I want to solve for dy dx, we will divide by 2y times 4 minus x. So my dy dx, my derivative, will equal 3x squared plus y squared over 2y 4 minus x. Okay, that's nice, but it did ask us to find the slope of the tangent at the point 2, 2. So we know that this first 2 is our x value and the second 2 is our y value. So now all we need to do is to plug in 2 and 2 for our x's and our y's. So we'll have 3 times 2 squared plus 2 squared over 2 times 2 times 4 minus 2. And when I do that, I will get 12 plus 4 over, let's see, 4 times 2 times 2 is 4, and then times 2 will be 8. So I'll end up getting 16 over 8, which will give me 2. So the derivative at the point 2, 2 is 2. Right, let's try another one. This should be a familiar looking problem. Find points where the graph has either a horizontal or vertical tangent line. Keyword in this one, tangent line. So I know that I'll be dealing with the derivative. So the first thing that I want to do for this problem is actually take the derivative, and we will do it implicitly once again. So the derivative of 4x squared will be 8x, and then plus the derivative of y squared will be 2y dy dx, because I am taking the derivative of y with respect to x, minus the derivative of 8x is 8, plus the derivative of 4y will be 4, but again, we're taking the derivative of y with respect to x, and then the derivative of the plus 4 will be 0 because it's a constant, and then it will equal 0. And then from here, again, I want to find dy dx, so I am going to subtract everything that does not have a dy dx on it, so I'll subtract 8x, and I will also add 8. Okay, so I will be left with 2y dy dx plus 4 dy dx equals negative 8x plus 8. I now notice that these both have a dy dx, so I'm going to factor that out. And when I do that, I will get 2y plus 4, and that will equal negative 8x plus 8. All right, from here, to get rid of multiplying by 2y plus 4, I will divide by 2y plus 4. So my derivative, my dy dx, will equal negative 8x plus 8 over 2y plus 4. Okay, so we found the derivative, but why did we find it? We wanted to find out where there would be a horizontal or vertical tangent line, and I'm going to deal with horizontal first. To deal with horizontal, remember we're trying to figure out where the slope would equal 0. So in this specific problem, I would want to know where would the numerator equal 0. So where would negative 8x plus 8 equal 0? So I'm just going to solve for x on this one. So then I end up getting x equals 1. So add x equals 1, but don't forget on this one, just because I found the x value, now I want to actually go back and find the y value. So we're going to go back into the original equation, so way back up into the original equation, and we're going to go ahead and plug in an x value of 1. So we're going to have 4 plus y squared minus 8 plus 4y plus 4 equals 0. Now I'm going to combine like terms, so I'm going to have y squared plus 4y, and then I notice that everything else cancels out, so I have equals 0. And then I've got y times the quantity y plus 4 equals 0. Notice I actually get two answers for this one. I'm going to get y equals 0 and y equals negative 4. So the points of the horizontal tangent lines are actually going to be at 1, 0, and then also at 1, 4. We're not done because we have not found vertical tangent lines, and hopefully you have not run out of room like me. Okay, vertical tangent lines would occur where the derivative equals undefined, which would make, that would be where the denominator equals 0. So we'll set the denominator equal to 0. And if I solved for y, I will get y equals negative 2. So now remember, once again, to get those x values, we're going to go back into the original equations to get the x value. So wherever I see a y, I'm going to put a negative 2. So I will have 4x squared plus, if I square negative 2, I will get 4 minus 8x plus 4 times negative 2 will be minus 8 plus 4 equals 0. And then let's see, we'll get 4x squared minus 8x, and once again everything else cancels out, so I get equals 0. So now I think I'll factor out a 4 and an x, and when I do that I'll get x minus 2. And then I notice that my x's will be 0 and 2, which means I will have vertical tangents at the point 0, negative 2, and also at the point 2, negative 2. So that's where I will have horizontal and vertical tangent lines. So hopefully now you can apply implicit differentiation to problems that we've worked with previously.